Hi, everybody. How are you doing? Thanks for joining the webinar. I'll go ahead and introduce myself. My name is Kevin Wood. I am the Director of Consulting Services here at Voltaiq. And with me today is Stephen Glazier, and we are going to go through DQDV and UHPC and give you some of the basics of these two really important and powerful techniques. So with that, I will go ahead and give you a little bit of background about myself. Like I said, my name is Kevin Wood. I have joined Voltaiq, been here for almost 2 years now. Before that, I got a PhD at the Colorado School of Mines. I was working in fuel cells and did my PhD in material science. After that point, I realized that I really thought that batteries were the wave of the future and wanted to try and work in battery technology. So I went and did a postdoc at the University of Michigan. Spent some time at the National Renewable Energy Lab as well, and then became a professor at San Diego State University, and then had a CTO gig at Solid Energies, which is a solid state startup company trying to take things from pilot to manufacturing, and then joined Voltaiq about a couple of years ago. So my focus is really in helping engineers try and make the most out of their battery data. There's so much insight tucked away inside your data, and most companies are not making money selling batteries, so their whole expenditure is going towards generating good quality data and trying to make insight from that. So how can we actually make the most of that data? Let's look at all of it. Let's make sure that you're actually getting as much insight as you possibly can out of that data. So part of the way that I do this is by helping people understand the physics and chemistry of what we're actually looking at, and then provide services to help people look at specific situations. So with that, we also do a bunch of research on trying to advance the current state of data analytics within the battery space. We have some recent papers on that. With that, I will pass it over to Stephen.
Awesome. Thanks, Kevin. So I'm Stephen Glazier, Director of Technology at NOVONIX Battery Technology Solutions. So I did my bachelor's in theoretical physics in Ontario at the University of Guelph, and then came out east to Dalhousie University in Halifax, Nova Scotia in Canada. Did my master's and PhD with Dr. Jeff Don. There's a photo of Jeff pulling a hat over my head at my graduation there. And then I joined NOVONIX shortly after that. So NOVONIX spun out of Jeff's lab in 2013. And since 2018, I've been here helping build up our pilot line, our prototyping line, that we do R&D services for the battery industry, helping people prove out their technologies, materials, et cetera. Built up a testing lab. We have over 3,000 channels on site here that we use for our services, and also help support our own materials divisions, both our anode and cathode divisions in Tennessee and in Halifax. My focuses here, of course, are on that prototyping and cell testing, understanding a lot of what's coming out of data. But another thing that NOVONIX is known for is our UHPC systems, our ultra-high precision coulometry systems. So a lot of my focus is in novel metrology techniques, understanding those data, and using those in new ways to get deeper insights into data and different failure mechanisms. That's going to come up a lot in the section on UHPC and how to get deeper insights out of data. Yeah, thanks, Kevin, and I'll pass it back to you. Take over and talk about DQDV.
All right, so thank you. So I will go through the DQDV section first, and then Stephen will hop in and talk about the UHP section next. We have hundreds of people in this webinar. It's good. There's going to be a variety of different places where people are at with their knowledge in the battery industry. So I figured we'd start with a couple key basic things. When you go to test a battery, there's two general modes with which you can test a battery. You can test it by controlling the current or controlling the potential. If you're controlling the potential, we call this potentiostatic. And in that case, you're actually controlling the potential of the battery. You're measuring the current response. Galvanostatic means that you're controlling the current of the battery and measuring the voltage response. So obviously, most of the time that you're doing battery cycling, you're doing galvanostatic cycling. So you are controlling the current. You're saying, I want 1 amp, I want 2 amps, or in a lot of times we think in C rates. So I want to charge my battery in 1 hour, or I want to discharge my battery in 2 hours, or whatever. And that sort of methodology is really applying a galvanostatic approach to cycling. So we'll talk a little bit more about those in just a second. There's also different testing hardwares. So you have a battery cycler, which is like a 2-electrode cycling system. So 2 electrodes mean that basically you're measuring the differences in potential between the anode and the cathode. And you can usually control both potentiostatic and galvanostatic. Then you have potentiostats, which add a 3rd electrode, a reference electrode in there. And they also frequently have what we call a frequency response analyzer, which allows you to apply a AC or sinusoidal current or potential measurement. And this is frequently used for doing EIS. Okay, potentiostats are a lot of times electrochemical tools, right? They're specifically geared towards doing electrochemistry, not just necessarily batteries. Whereas battery cyclers, a lot of times are geared just towards doing battery testing. Battery cyclers are usually a little less expensive. Potentiostats are a little more expensive. And there's a variety of reasons that you could, want to use those different types of equipment. What I'm going to be showing you today is going to be focused from DQDV perspective. You can do it with a battery cycler or with a potentiostat. Frequency response analyzers are not as important. Okay. With that, I'm going to move to the next slide here. So let's talk a little bit about what galvanostatic cycling looks at. So galvanostatic cycling, like I said, you apply a constant current here. As that constant current is applied, the voltage of the battery is changing. And this voltage of the battery changes for a variety of different reasons, right? And we're going to go into that. But essentially, it comes back to three main things. It comes back to thermodynamics, kinetics, and transport. Those are the reasons that the voltage within a battery changes, and we'll dive into that. And basically that voltage change is the key thing happening within the way that what we're going to be analyzing with DQDV. Okay, so we hit this point right here, and then there's a rest step here, and then we go and we do constant current discharging here for an extended period of time, and then we hit our rest step. So this would be like an entire cycle of galvanostatic cycling. Now, there was a question that just came in the chat about how do you calculate charge and discharge capacities. So it's usually the integration of the current right here underneath in time, and you get the amount of capacity that has been passed by that system, and you can compare that from charge and discharge. And when Stephen gets to talking, he'll talk a lot about how NOVONIX has really high precision equipment to be able to really accurately measure those and measure the difference between charge and discharge, right? Which a lot of times we call Coulombic efficiency, but there's a lot of additional information that we can get out of those types of measurements as well. Okay, potentiostatic charging, a lot of times we don't use just potentiostatic charging, but if you did, this would be what it would look like. You'd hold your battery at a constant voltage, right? And the current would change dynamically like this. You would hit a rest step then, and then if you held at a constant voltage on discharge, it would look something like this. You hold it 3 volts and the current changes like this. It's an exponential decay. This is only really used in lead acid battery charging. Maybe there's some other things there as well, but not super commonly used just by itself in the battery industry, in the lithium ion battery industry. Most of the time where we see the combination of potentiostatic cycling get included here is when we go to do these galvanostatic, like a constant current charge with a kind of taper charge at the very end. So what happens is that you normally cycle at a galvanostatic current, so a constant current right here, and then eventually you're going to switch towards, let's say you hit 4.1 volts as your cutoff voltage right here. So you're basically saying, hey, I want to charge until I hit 4.1 volts. As soon as the voltage hits 4.1, you switch and you say, now I want to hold at 4.1 volts and I want to see how the current now changes, or I'm going to keep going at that holding at 4.1 volts until the current has decayed to some set value. A lot of times it's C over 20 or something like that, right? And then you move towards a galvanostatic discharge, and usually there's no sort of constant voltage discharge step. We usually only do that on charge. That's for a couple reasons. Make sure that you get your batteries charged as you possibly can, and also to try and limit the effects of cycling at a high C rate at the upper voltages as well. A couple different reasons there. People focus on that. All right. We're going to talk about DQDV. So this is all set up to talk about DQDV. This is the last setup slide before we actually show DQDV and talk about what it is. DQDV really focuses on how the voltage changes during a cycle, as I alluded to. And the voltage during a cycle can change for a variety of different reasons. And so I want to lay out what those reasons are before we start talking about DQDV. So one of the most foundational and important reasons, the reason that LFP batteries have a different potential than NMC batteries, which have a different potential than sodium ion batteries, than lead acid batteries. All of those relate to the actual chemistry and the thermodynamics and the potential difference between the anode and the cathode. Okay, so those changes in what we call standard electrode potential are really important and form the foundation of the voltage profile that you see when you plot voltage versus time for a specific cycle. Okay, then we have, so that's just sitting there. That's why when you measure open circuit voltage, you measure what the thermodynamics is actually telling you, right? The difference between the anode and the cathode potential. When you actually go to use your battery, right? We actually want to use our battery. We don't want to just have it sit there and look pretty. We actually want to get energy out of that battery. So in that process, we have to sacrifice some voltage, right? We actually have to, if you think about if you remember back to thermodynamics or maybe a kinetics class or something like that, we've got these energy barriers, right? And you have to get the ball over the hill to get it to roll down the hill. So you have to sacrifice a little bit of energy to actually drive this reaction. Get the lithium from the anode in this case. Let's say we're going during discharge. You want to get the lithium that's tucked away in the anode, right? You want to take it from lithium in the anode to actually a lithium ion in the electrolyte, right? That's called a charge transfer reaction. And there's kinetics associated with that. And there's going to be losses associated with that process. We have to give up a little bit of voltage, right? Then we have to move the electron or the ion, right, across the actual electrolyte. Okay, and in this process, we have to move it where it needs to go. There's losses that are going to occur there. Now, once it gets to where it's going, there's also going to be some other transport losses we'll talk about in a second. But you can think about just moving that lithium ion across the electrolyte. There's losses associated with that. Just there's resistance associated with moving an electron through a wire. Okay, then when you get to now wanting to put that lithium ion into the cathode, all right, we have a lithium ion and we want to make it lithium in the cathode. So there's a charge transfer reaction once again that has to happen there. And you basically sum all this up. So if your thermodynamics said, hey, my open circuit voltage was like 3.7 volts, and then depending on how fast you're wanting to do this and the C rate that you're at and all of those things, there's going to be all of these losses get summed up, and eventually you get the voltage that the system is actually going to be at, okay? Outside of this, another thing that can change the voltage profile, so outside of the normal idealized battery reactions that are happening, outside of those, there can be other processes like corrosion and things that we probably don't want to have happen, right? Maybe it's an SEI forming on some sort of one of the electrodes or something like that, right? But there can be other things, other reactions happening that can cause changes in the voltage profile. This is just laying out the theory of why voltage changes as you cycle your battery. Okay, I'm going to pause here for just a second and see if there are any questions. So somebody asked, does battery capacity, the size of the system, have any relation to which method you choose, galvanostatic versus potentiostatic? And I would say no. You basically are going, because batteries are a closed system, you really want to focus on operating in galvanostatic mode, right? Different electrochemical systems, specifically open electrochemical systems, there's different, you may want to do something different, right? One of the key things that we'll talk about here is that in the electrochemical community, a lot of times people focus on CV or cyclic voltammetry. And cyclic voltammetry is really a voltage controlled or a potentiostatic method that is widely used in the electrochemistry industry. Because batteries are a closed system, we really want to focus on utilizing galvanostatic control, and DQDV allows us to utilize galvanostatic control, but get very similar information to what you would get in cyclic voltammetry. If you're an electrochemist, you know what I'm talking about. If you're not, then don't worry about that too much. Okay, so let's go to the next slide here. All right, so I have a question for you. So before we jump in and actually start looking at DQDV, all right, here is a poll. So go ahead and try and answer this poll. We can't see how you vote, so don't worry about that. But this is just going to be helpful for me to know the range of knowledge on DQDV out there. It's also, I think, helpful for people to know. So a lot of times people sit there and go, boy, I don't really know a lot about DQDV. Maybe I should try and be quiet about that. And you'll realize that there's probably a lot of people here that don't necessarily know a lot about DQDV. I'll give you guys just a second to answer that question. And while you do, I will take a look at some more of these Q&A that have come in. Okay, so one of the questions that has popped up is that what's the difference between this in the kind of a laboratory setting and the real world? So obviously, like when you step on your gas pedal in your car, it's like you're setting a current, right? So you're basically stepping on the gas pedal and you're going to apply a specific current. Now, obviously that changes. The way that we do a lot of battery cycling is we basically hold at one constant current. That would be like driving at a consistent speed, basically setting cruise control on your car and driving on a flat track. So obviously, as you cycle batteries in the real world, there's a lot of changes, but all of those are galvanostatically controlled because the current is being set, right? Pretty much the only time, I'm sure that there's probably some exceptions to this, but the main time that you're going to see that voltage control, that potentiostatic control, is going to be during the charging, the very final step of the charging phase. And sometimes during like a tap charge, during the formation process, during battery manufacturing. Okay. So it looked like there was a range of options. It looked like Fluent and User were pretty common. That's great. There's about 5% of you out there that are going to try and catch me and trip me up, so that'll be fun too. Let's see here. So let's talk about understanding DQDV. Okay, so I have to first throw out a big scary equation here. If you're familiar, this is Gibbs free energy. This is the Gibbs free energy equation, talking about basically looking at Gibbs free energy from the standpoint of chemical potential. If you're not super familiar with this, don't worry too much. Essentially, we can go from Gibbs free energy to the potential at individual electrodes. Okay, so this is a kind of an important point. Anytime you want to go from the world of chemistry, which is, we're talking about Gibbs free energy, we're talking about thermodynamic state functions, those sorts of things, right? And there's a lot here. I could give you an entire several days worth of material just on understanding thermodynamics. So that's not the point of this, but because thermodynamics are so important, I want to lay this foundation here. If you need to have more questions on this, we can dive into that, or you can dive into that at a later point. But essentially, when we want to go from the world of chemistry to the world of electrochemistry, we want to use this term right here. We basically want to use Faraday's constant and the number of moles of electrons to help drive us there. And so we can do that. We can basically convert Gibbs free energy into potential. And when we do that, basically we can see that the two sides of this equation tell us different things. The left side here, which is talking about the actual chemical potential, and we're just changing the number of species there, that chemical potential is really going to be the effects of the chemical reaction. So this would be like LFP versus NMC versus maybe at an anode, you're talking about graphite versus silicon, right? So whatever the potential of that individual electrode is, which I'll show you examples here in just a second, okay, that is going to be driven by this part of the actual equation. Then the right side of this equation is really where the effects of concentration come into play. And the effects of concentration coming into play basically give a traditional battery shape. This is where it is exponential, and then it's a little bit flatter, and then it goes exponential again. Though that traditional shape is actually due to the moving from a lot of reactants and no products to a lot of products and no reactants. Okay. So when you actually, these are in potentials, right? So if we have the difference between the products and the reactants, this is going to give us the cell voltage. Basically, the superposition of the anode and cathode is going to be what gives us the actual voltage of the cell. I've created down here is a hypothetical example in an idealized world, just showing you what this might look like. So we're going to use a phase diagram here, which people are probably familiar, probably seen some sort of phase diagram. Let's say we're cycling. This phase diagram right here basically takes you from completely discharged all the way to completely charged for some hypothetical battery. What you can see here is as we go from room temperature, if we start here at the very left side, we're going to go through the alpha phase, and then we're going to go through the alpha and beta phase. As we go through the alpha phase, you can see that the potential is increasing slightly. Then there's like kind of a sharp knee here as we go towards the alpha and beta phase. And then when we're in that mixed region, we actually have a very flat voltage profile. Okay, and we can talk about that in just a second. It comes from the Gibbs phase rule. And then as we go through this, we actually change the concentration again, and this leads to this beta phase. In this beta phase, you can see we have a sloping voltage profile. Then we reach a mixed region again with alpha and beta. That mixed region means that we're going to have a flat voltage profile. Then we have another knee, and then this kind of increasing gamma phase here as well. So where this actually comes from, okay, is that the reason that you see things as flat, very flat, or maybe just slightly increasing comes back to the Gibbs phase rule, which means that the degrees of freedom are dependent on the number of components in the phases that you have in the system. So phase mixtures are going to have very flat voltage profiles, right? Whereas single phases are going to have kind of those changing voltage profiles. So plotting these incremental changes, so if you see here, and if we talk about this right here, so this would be a change in capacity right here, right? If I plot this, this is a state of charge. You could plot this as time. You could plot this as capacity, basically on this x-axis down here on the right graph. All right. When I do that, you can see that this is a large change in capacity right here. When we talk about DQDV, we're talking about DQ stands for change in capacity, right? And DV stands for change in voltage. When I have when I'm in these mixing regions, essentially what that means is that I'm going to have a really large change in DQ, and I'm going to have a very small change in DV, which is going to lead to a very sharp peak. in DQDV at that voltage. So let's take a look at what this actually looks like as we move forward. Before I can do that, though, I have to touch on one thing here. This is the difference between 2-electrode and 3-electrode measurements. I alluded to this earlier. And the reason that I'm going to do this isn't necessarily from a practical standpoint of, oh, I think you guys should all do 3-electrode measurements, but it's so that you understand when you look at the DQDV profile, you're actually able to understand where these things are actually coming from, okay? The reference electrode in a 3-electrode cell is assumed not to change. The potential of that reference electrode, the theory is that is not going to change, and it's going to be consistent during the entire reaction. Because it's consistent during the entire reaction, we measure voltages, right? I can now measure the change between the potential at the anode and the potential at this reference electrode. That's now a voltage, but because I know that the reference electrode potential is not changing, I now know I can back out what the potential of my anode is. So, or my cathode. So in this case, I have, using a 3-electrode cell, I was able to figure out what the potential at my cathode is. I could also figure out what the potential at my anode is. And then when I bring these all together, if I were to do a 2-electrode measurement and basically take out that reference electrode, I would get the superposition, basically the difference between the anode and the cathode here. Okay, and this is going to give you what your cell voltage is going to look like. When I go to look at my DQDV profile, what I'm going to see is that I'm going to have peaks that are associated with cathode reactions, and I'm going to have peaks that are associated with anode reactions, and they're going to be mixed together in my 2-electrode system. So to help better understand that 2-electrode system, which is probably what most of you are going to be using, right? It's really helpful to have some idea of how the 3-electrode system works so you can understand that superposition or convolution. Okay, so now let's actually look at DQDV. So here, normally people have different opinions and there's different thoughts out there, but a lot of times people will plot DQ, so DQ divided by DV, and they'll plot that on the y-axis, and then they'll plot voltage on the x-axis. Some people will talk about state of charge on the x-axis. There's different opinions out there. We can talk about those in just a second. Because of voltage being on the x-axis, your traditional voltage versus time plot is going to go from this direction. It's going to be shifted like this. It's going to be turned 90 degrees. And so that's actually what we're looking at here. And this is a 3-electrode measurement of a graphite anode. Okay, and so in this process during charging, so we're going to lithiate, we're basically going to start at a voltage up here and we're going to move this direction. And as we do, the voltage of that system is going to change and we're going to go through these nice voltage plateaus. And now you can understand when you look at these voltage plateaus, we're in a region of mixing. Okay, is really going to be where we're at. And the mixing that's actually occurring here is we're going between stage 1, which is where there's no lithium, stage 2, which is where there's lithium every 3 or 4 sheets of graphite, right? Then stage 3, and then stage 4. Okay, and each one of these peaks corresponds to a mixing region of this actual, of the lithiation of the graphite anode. Okay, so this is looking at 3-electrode data from the graphite anode. Okay, I saw a couple questions came in, so I'm going to pause for a second and see if this is a good time to address those. Yeah, so one of the questions is, so blah, blah, blah. Yeah, okay, so one of the questions here is saying, how can I try and get, instead of full cell data, how can I do half cell potentials? So the reality is that you have to have a separate cell to be able to do 3-electrode measurements. There's a lot of challenges associated with that, which I don't have time to get into right now, but there are a lot of challenges associated with 3-electrode measurements, but it would be great to have 3-electrode measurements and to create a library of that. And then, as I'll talk about at the end of this, it would be great to be able to then deconvolute those maybe by peak fitting or something like that, but a lot of times that gets pretty complicated. So I'll give you some tools maybe at the end of this to help you understand how we might be able to look at this. There was another comment here about sometimes people call this incremental capacity analysis. There's lots of different terminology that can be used out there, but the general concept is the same, and understanding this, whether you call it DQDV, incremental capacity analysis, differential capacity analysis, things of that nature. Okay, let's see here. There's a lot of things coming in. I don't have time to get to all of these. There was also a question about smoothing. That's a good question here. Yeah, so a lot of times when you plot DQDV, depending on how the data was recorded from your cycler, a lot of times if it's recorded in time, there has to be a smoothing process that is done. So depending on the resolution of your cycler, there's different smoothing levels will work, usually 1 to 10 millivolts. somewhere in there is a good smoothing algorithm. Okay, let me move on here. So now let's talk about looking at this at the cathode level. All right, at the cathode level, we were interested in understanding how lithium is put into or out of. In this specific case, I'm going to talk about the layered cathode system. So this is the NMC cathode system. And as you go through that process, there's different phase transitions. There's a hexagonal phase, and then once you've removed a certain amount of lithium from that, it transitions to a monoclinic phase, and then it goes back to a hexagonal phase and a slightly different hexagonal phase. There's these different transitions that actually go through here. When you look at just 3 electrode data, you can see for most low nickel content NMCs, we're pretty much only going to go through, be able to access, right, that first transition. So basically going from the hexagonal phase to the monoclinic phase. That's pretty much all that we're going to be able to access initially. And so as we do that, we're not able to access these other phases because the voltages would get too high. We drive oxygen evolution. We'd have basically structural collapse. So as we go to higher and higher nickel contents, it basically brings the access to those voltage transitions down into lower voltages. And now for the same amount of voltage going out to I think this is 4.4 or 4.35 volts here, right? You can now actually start to see that we're able to access more of the lithium from within this structure. That's the big benefit of going towards nickel. And you can clearly see that in DQDV because DQDV is helping you understand and see the thermodynamics of the reactions that are taking place here. Okay. The Q&A is blown up here, so I'm not sure I'm going to be able to get to everybody's questions, but hopefully I'll be able to answer these, and I could take a couple breaks here in a little bit to try and find major themes in the Q&A. Okay, so now let's talk about putting this all together, right? DQDV, and another one that we haven't talked about right yet is DVDQ. A lot of times people really have one opinion of the other, whether they should use DQDV or DVDQ. You can use both of them. They both give very similar information. So we can talk about that in just a second. But essentially, when you go to mix, so we had the 3 electrode data, right? So like somebody was alluding to in the Q&A, right? I don't have 3 electrode data. I have 2 electrode data. What do I do? Now it's basically going to be a superposition, right? You're going to be mixing and blurring these. So if I take basically this graphite that I have here for lithiating, and I take some sort of low nickel content NMC, and I mix these together, what you're actually going to see is you're going to see a peak that looks like this. So this black curve down here is now the DQDV. So instead of having 1 peak like I had for just the cathode and 3 peaks like what I had for the anode, now I see I have 2 peaks because they're all blurred and mixed together. And so it can be a little challenging to pull these out. As you get really good at looking at these, you can understand exactly what's going on. I can look at a lot of these systems now and tell, oh, this looks like a low nickel content material and they're using a graphite anode, or maybe they have some silicon. So as you get more and more familiar, you don't necessarily have to do peak fitting or anything like that to be able to understand and tell the chemistry. You can see and understand by just looking at the general shape of the curve. Another thing to point out is that peaks in DQDV typically represent like I was saying, the mixing regions, right? So somewhere where you're between stage 1 and stage 2, or stage 2 and stage 3, or H1 and M, or something like that, right? The peaks are usually associated with that mixing region. In DVDQ, the peaks are usually associated with the transitions between those regions, if that makes sense. So you're more at the start or the genesis of a phase rather than in the middle of the utilization of that phase, if that makes sense. So that's part of the differences, right? Like I said, the information a lot of times is communicating very similar information, but just the presentation is a little bit different. Personally, I really like plotting DQDV and DVDQ versus voltage or OCV, which we'll talk about in a second. And that's because it gets back to the underlying thermodynamics and physical manifestations of the system itself. Some people like plotting it versus SOC. I'll show you a graph for that in just a second. Okay, here's another way of looking at this. Here is looking at an LNMO system, much higher voltage. You have these 2 clear differences in voltage. You've got the DQDV in the middle there and the DVD further to the right, and then an understanding of the different phases that are going on there. And then you can really see how when you mix this together, so the full cell voltage down here at the bottom, how this changes the behavior and the look of the actual system itself. So once again, it's really helpful to have a library of these 3 electrode measurements to be able to help you really understand when you look at a two electrode cell, what's actually going on and the underpinnings of some of this. Okay, so let's talk about looking at dVdq and DQDV versus SOC. So here I basically plotted very similar information to what I was showing you before, but now instead of plotting it versus voltage, I plotted it versus SOC. You can see that there's a pretty significant change in the appearance of this. A lot of times people do this when they talk about doing things at different C rates and they want to plot things for different C rates. They can tell different pieces of information when things are plotted at different C rates. I'll go into C rates here in just a second, but just to throw that out there that this is another way that people can use this system. All right, so I'm going to go ahead and pause. I'll try and take a look at the Q&A while you work on answering this question, and I will be right back at it. Okay, so here there's a couple of questions. One is, if I want to understand the peaks, can I refer to scientific articles to characterize aging? Yeah, it's great. There's scientific literature can be hard to peel through. Is it two electrode? Is it three electrode? Is it the exact same system? What C rate is it at? Just be really rigorous with the sort of stuff that you will accept, if that makes sense when you're looking at literature. So just make sure that I'm only going to look for three electrode measurements that are at this C rate and whatever the case may be. When you confine it and look at it in that way, it can be, I think, much more helpful. Yes, scientific literature can be helpful, but you have to have good bounds on what you're looking for. And I would, if it's at all possible, I would encourage you to do your own experimental three electrode measurements and have a library functions. Don't spend a lot of time on it, but basically create some of those functions so that can be a very helpful strategy. Or find somebody that has a good library of functions as well. Okay, I'm really sorry I'm not able to get to this. Somebody's asking, is dVdt and dVdq the same? They are not necessarily the same, although they can have very similar information in them. One of the places where dVdt and dVdq would not be the same is at rest. You would see dVdt will still have values associated with them. And so a lot of times people talk about using dVdt to monitor rest potentials and see how the voltage changes during a rest step. Obviously, dVdq would not give you the same information in that case. Okay, yeah, and then there's also terminology here. Is capital D, capital Q, capital D, capital V the same as lowercase d, capital Q, lowercase d, capital V, or if you put it, yeah, they're all the same. All of those are the same thing, right? Just people have different terminologies. So there's a lot of different ways people will represent that. Some people call it DCA, some people call it ICA, right? There's a lot of different terminology floating around out there for essentially the same type of analysis. Okay, so yeah, DQDV, the peaks in DQDV, most of the time that the peak itself is associated with a chemical reaction, right? We're talking about it comes from these individual phases. That's the reason that there's a peak in DQDV. Now that peak can shift because of kinetics and transport and other properties, which I'll show you here in just a second. But the reason that the peak exists is because of the chemical reaction. Okay. So let's talk about what does two electrode DQDV actually look like, right? So let's talk about a few different systems here. Here is DQDV for an LFP cathode and a graphite anode. You can clearly see, because LFP has a nice flat voltage profile, you can really see pretty clearly the peaks that are associated with that graphite anode, more clearly than you can in a lot of other systems, just because of how the energetics kind of line up there. In going towards the bottom one down there, so looking at the red curve, this is a little bit higher nickel content NMC. You can see that you pretty much have those two peaks there that are associated. That first one is mostly associated with a transition between the graphite. So a lot of times that first peak is associated with, people call it associated with graphite. Second peak is more associated with the NMC, although you can obviously tell from what I've showed you in the previous slides that there's this mixing and kind of complex interplay going on there. And then the LMO at the end helps raise that voltage out, or raise that DQDV out towards 4.2 volts. When we go to the green one there, this is an NCA chemistry. You can obviously tell that there's pretty high nickel content because you're able to get a lot of capacity out of the system at those higher voltages. Same with the NMC. The thing I'll point out here is that look at the shoulder that you see around 3.4 volts there, right? So in both the blue and the green, that you have a shoulder around 3.4 volts that you don't really have in the red sample here. That's indicative of a silicon anode being used in these types of systems. The peak position here, if you're measuring it over time and you're measuring intensity over time, that can help you identify the degradation of specific chemistries potentially, or how that system is evolving, or if there's overpotential buildup specifically with regards to specific phases, or at the anode side more than the cathode side, things of that nature. Okay, now let's talk a little bit about the effective C rate. So the effective C rate, so I've got a 2-electrode measurement here. This is on a Samsung 50E cell, so this is an NCA chemistry. You can tell that, maybe not from this. It also has a little bit of silicon, as you can see by the little shoulder down here. And now I'm looking at 2 different C rates. So I'm looking at one that's at 0.1 C and one that's at 1 C. So one of the questions that was in the chat was, what's the effective C rate? What's the ideal C rate to do DQDV at? The answer to that question is really you should try and minimize the C rate as much as possible, but obviously when you do that, the amount of time that it takes is much higher. Kind of a traditional DQDV is probably C over 10 or 0.1 C. That would be a kind of a standard that people use, but you can see the effects here, right? If I go to 1 C, you can see how the peaks have shifted. The peaks have shifted because now it caught more overpotential, right? The kinetics and the transport, those things that we were talking about, how they affect the voltage profile, those things have really shifted how the battery system behaves. And in that shifting process, you see these peaks actually getting to move. And the faster, the higher C rate you go to, the more these peaks are going to shift. And when they shift more and more, it could actually change the reaction pathway. So now maybe instead of something wanting to just go into one phase, because it has more energy, it could actually go into another phase at the same time. So maybe you're putting, instead of just into stage 1 or stage 2 or stage 3 or stage 4, right? Now maybe you're putting it into 2 different phases at the same times. And so there's going to be these blurring and mixing of reactions as you go to higher C rates. There's a question that somebody already alluded to in the chat of, okay, what's the best way to do this? How can we try to minimize the effects of kinetics and transport and just see the effects of thermodynamics? How can we try and then see just the effects of thermodynamics and transport? What can we do? I won't talk about how we can minimize and look at the effects of just kinetics and transport. That'll be a different topic for a different day. But how we can try and understand just the effects of thermodynamics is basically do a whole series of pulses, right? You can do these at a bunch of different C rates, and as long as you allow this system to actually come back down to thermodynamic equilibrium, the C rates aren't going to matter, because essentially what you're going to be looking at is you're just going to be looking at the thermodynamics. So the reason voltage changes, I got to move my thing here, the reason voltage changes as a function of after you've removed the current, so here I have a pulse, whoops. Here I have a pulse, and I've removed the current right here. And after I've removed the current, the voltage continues to change. That voltage continues to change because of kinetics and transport. Eventually, that voltage stops changing. When the voltage stops changing, now you've reached a point of rest. And now you're looking at just how much did the thermodynamics change during that pulse. And if you do this a bunch of times, we're talking maybe 40 to 50 times, over an entire charge and discharge cycle, you can actually now take this pulse as dq, right? You can now take the length of time if these pulses are capacity controlled. You can take that as dq, and you can measure how much voltage changed from OCV point to OCV point. And now you're looking at just the thermodynamics instead of the kinetics and the transport. So this is a powerful tool to help you reconstruct these DQDV plots, but only look at the contributions that are associated with the thermodynamics, okay? And so when you do this, you can now see that looking at this SDQDV, we call it SDQDV or static DQDV or open circuit voltage DQDV. Now you can see what these peaks are actually looking like, and you're looking at the actual thermodynamics of the system instead of the convolution with kinetics and transport. I'll go ahead and throw a quick question out there on the SDQDV stuff and take a look at see if there's any more questions here in the chat. Yeah, so somebody's asking about, can you take a look, share some insight about peak intensity? Yeah, specifically during aging. Yeah, and I think that you'll specifically be interested in some of the stuff with UHPC because there's going to be a lot of really cool techniques that they have to help try and see where different coulombs are going within the process. But obviously in DQDV, if you see the peak intensity change, that's telling you that you've lost lithium that is either coming to or that is either going to or coming from that specific phase reaction, right? Maybe it's being redistributed, right? So maybe you have some sort of structural collapse and maybe it's now going into some kind of different phase, or maybe you lost that lithium entirely and now you actually have lithium loss. So there's active material loss and there's lithium inventory loss. And you can see both of those things are going to be, you're going to observe both of those within the peak changes within DQDV. Okay, and then let's see here. Yeah, so somebody was asking, is the SDQDV similar to GITT? And the answer is yeah, it is very similar to GITT. We have a different protocol that we call app that we use. We have a paper on it, which you could probably find somewhere else. But GITT will basically give you the same information that we just did. If you basically allow your pulse to relax and you measure and you do capacity controlled pulses for GITT, you measure the capacity change and the voltage change, you could reconstruct this SDQDV plot in the same type of way, right? So yeah, you can use GITT, basically perform this analysis. It's adding extra analysis on top of what's normally done within GITT. We use the different current pulses to be able to help us gain more information about different systems. Okay, I'm almost done here, but specifically now once you've gone towards the actual thermodynamics of the system, it could be beneficial to do some peak fitting here. So here's peak fitting, basically trying to fit the actual SDQDV peak. Okay, where are these different reactions coming from? What reactions at the cathode and the anode are responsible for this? Because it's at actual thermodynamic equilibrium, we can calculate out a delta G for the actual reactions, right? That's the difference between the anode and the cathode potential there. What's the delta G for that reaction? And you can see how remarkably stable these are and consistent these are because they're actually at thermodynamic equilibrium. Probably some of the slight variations here in the actual voltage is due to very slight variations in the thermo and the temperature that the cell is at locally, just depending on whether it's charging or discharging. So this is a helpful tool, but I want people to know that anytime you start going with peak fitting, this goes for if you're doing XPS or some sort of spectroscopy or anything like that, whenever you get into peak fitting, it's fraught with potential error. There could be a lot of variations. It's just trying to do the best that it can to fit the data. So you have to look at it with a little bit of a critical eye and see if the results that you're actually getting make some sense. So just be careful when you do that. Here is the final question for me. True or false, peak fitting DQDV curves is a simple way to understand what is happening within your system. Let me look in the chat and see if we've got a new... Does DQDV help identify lithium plating? The answer to that could be potentially. You would have to have a significant difference in the potential at the anode or the potential at the cathode if you're plating lithium. So most of the time you're going to be plating lithium at the anode. And if there's a change, a pretty significant change when that reaction pathway changes, so basically going from lithiating graphite to plating lithium out, then yes, you could observe that. There's also a lot of work out there on using DVDT, specifically within rest steps, to also help identify lithium plating as well. So that may be something that you would be interested in taking a look at. Okay, so yeah, DQDV, fitting DQDV is wonderful. I would not call it a simple, easy way to understand your data because there's so much that goes on there. It could be pretty complicated and confusing. So just want to make sure that you understand that caveat. It could be powerful, but also kind of make sure that you look at the results with a skeptical eye. All right, so this is about it for me. Basically, DQDV, there's a lot of dynamic behavior. When you do traditional DQDV, just realize you're looking at the thermodynamics. That's what the peaks actually come from, but then the peak positions and intensities shift because of kinetics and transport. The peaks themselves, like I say, can indicate amount of capacity that's coming from a specific reaction. Peak shift as peak changes as effects of degradation and overpotential and transport change. And then static DQDV, that SDQDV, really helps you understand the effects of just the thermodynamics and removing the kinetics, but gives you basically the same sort of DQDV plot that you're used to looking at. With that, we'll open it up for more questions later. But with that, I will pass it over to Stephen.
Awesome. Thank you very much, Kevin. I'm just going to request to share my screen here. Take over. All right, thank you very much. I was trying to keep up with some of the questions there, and I typed some answers in there as you were going. So hopefully that helped with a few of them. All right, we'll get started in here and talk about ultra-high precision coulometry and really start with the basics, pick up where Kevin left off. And this is going to be fairly complementary to what Kevin was talking about. We were talking a lot about voltage measurements and raw data and transformations on the raw data to get insights. And I'm going to transition a little bit and talk more about current and counting coulombs and using cyclometrics to get other types of insights into data. And really, there's a focus here on doing this very accurately and precisely. So NOVONIX offers ultra-high precision coulometry equipment, which is capable of doing these really accurate and precise measurements of current and voltage, which really enable some of these insights. So I've got a question up here for everybody for a poll. Have you ever used ultra-high precision coulometry test equipment before? We'll get into what ultra-high precision means. So if you're not really sure what that means, you can answer unsure. And yeah, we'll see what the variance within the audience is. Okay. So we'll move on from there. So I'm going to start with a brief introduction, picking up where Kevin left off with cell testing. We already talked about galvanostatic testing, so I'm going to actually use that as an example, again, to talk about Coulomb counting this time. Instead of looking up at what's happening at our voltage curve, let's look at the information that we can get from actually counting these electrons we're moving through the circuit. So we've talked about this charge and discharge, measuring the voltage response to the current, and how we get some of these cyclometrics by integrating the current over time, like charge and discharge capacity. And now the trick is with some of these pieces of information is if your measurement of current and voltage isn't accurate or precise through these raw data measurements of time, voltage, and current, then this error or uncertainty kind of propagates through these calculations. You're integrating over all of these errors. And if you're over counting during charge or under counting during discharge, these deltas really add up, and this can really affect things like coulombic efficiency. And of course, we then take these data and we infer things that are going on within our cells, either with raw data or aggregating this into cyclometrics like capacity retention, energy, average voltage, delta V. And we look at these and see where capacity is going in our cells. And of course, everyone's probably aware that this style of testing, especially when you're trying to prove out the longevity of a certain chemistry or look at warranty considerations for a certain application, this can take months or years. And really the questions that were asked when UHPC was being thought up and trialed within Jeff Dahn's lab 15 years ago or so was, how do we do this faster and more efficiently? Is there something that we can do with electrochemical testing to get more insights by doing the same types of tests? So to answer this question, I like to think a little deeper about what we're really measuring when we're testing a cell. We're measuring that potential response to a current that we're putting through the cell. And when we usually look at these diagrams that we're all very familiar with, we talk about moving electrons through the circuit and lithium moving from the cathode to the anode during charge, and vice versa during discharge. But really, what we're directly measuring when we're testing a cell is that potential difference between the electrodes and the electrons moving through this external part of the circuit. We infer that this is due to lithium moving within the cell, but there's a whole bunch of different mechanisms that are occurring that can contribute these electrons being counted during charge or not counted the next cycle. So I like to really think about just this part of the circuit when I'm interpreting my data, because really in here, there's a whole bunch of stuff that can be contributing. So to build this out, I'm going to just show what happens during charge because that mitigates a lot of arrows pointing in every direction. So we're all very familiar with capacity loss. It's what we look at over time as cells lose capacity, some faster than others. And there's some well-known sources of capacity loss like SEI growth, active material loss, impedance growth, and all these mechanisms lead to capacity fade. And so what this looks like during charging a cell is we're extracting lithium from the cathode by putting a current through the cell. And then this lithium either circulates into our anode or maybe gets lost into SEI reactions. But we're counting each of those electrons that we move through based on those lithium that we move across the cell. And then even from one charge, the subsequent discharge cycle, we may lose some of this capacity. And so that's going to create a mismatch between our discharge capacity and our previous charge capacity. And so I'll introduce here Coulombic efficiency, which is the ratio of a discharge capacity divided by the previous charge. And so for a perfect cell, a cell that doesn't have any degradation, this would be 1.0000. And so if we're losing capacity each cycle, we can kind of tack on this fade term to describe this difference from one that may happen each charge-discharge step. And so we're all very familiar with using CE in this way, but there's a lot of other reactions and mechanisms that can contribute us to counting an electron through the circuit during charge. And so I want to introduce a bunch of other mechanisms here and how those might influence how we interpret data. So this diagram gets a lot more busy here when we look at all these other types of mechanisms. So sources of other electrons just during charge is what we're showing here. Can be things like electron donating reactions, electrolyte oxidation, shuttle mechanisms within the cell, transition metal dissolution, and short circuits or self-discharge. So in some of these cases, if we look at manganese dissolution, to create charge balance within the cell, we actually have to remove an electron, count this through the circuit during charge with a self-discharge mechanism that I've drawn in here just as a resistor through the cell. We're actually just creating an electron shuttle around the cell. As we're charging the cell, we're counting excess electrons through the circuit. With a reversible shuttle mechanism, there were some interesting papers published by Jeff Don's lab talking about PET tape introducing reversible shuttles within cells. And they realized this using high precision equipment. And this, again, just creates this electron shuttle that we end up counting these excess electrons during charge. And reversible electrolyte oxidation, where we oxidize an electrolyte species, and to create charge balance, we move an electron through this circuit. All at the same time, while we're extracting lithium from our cathode, we're still inserting it into our anode. So we're moving a lot of electrons through the circuit that may not actually be due to reversible lithium intercalation. And I say a lot, but we all know this is actually a very small amount. The majority of what's happening is this reversible lithium intercalation. But what this means is there's this other mismatch between electrons that we count during charge and electrons that we count during discharge. During discharge, all of these things just look like a self-discharge mechanism where we lose out on counting them the other way around. So this means there's this other term that we can tack on to Coulombic efficiency here and actually have multiple contributions to a decrease in Coulombic efficiency. So we've got this fade term due to those fade type reactions due to lithium inventory loss, and then this slippage term, which can be due to these additional things that are happening in the cell. And you'll notice that these additional electrons that we're counting through this circuit, within the boundaries of these individual mechanisms here, there's actually no lithium being lost. What this means is over time, we may not see any of these mechanisms if we're only looking at capacity fade. And some of these things like electrolyte oxidation, which can cause salt depletion or manganese dissolution, over time can create massive impedance buildup and ultimately lead to cell rollover failure. Even though we can't necessarily see any lithium loss in early cycles or any kind of capacity fade, these can lead to that kneeing failure that's very hard to predict. So if we can accurately split up these different types of mechanisms, this is a little bit of a teaser for later, we can actually really accurately predict when some of these types of failures and kneeing rollover are going to happen. So a big question that comes up is, okay, all of this considered, can we actually measure these mechanisms? Can test equipment do this? Because some of these things are very small. Can the resolution, the precision, and the accuracy of current and voltage allow us to do this? And some back of the envelope math would tell us that if we wanted to, very early in cycle life, predict the difference between 800 and 1,000 cycles to 80%, that we would need to be able to measure the difference in Coulombic efficiency of 0.99972 and 99978. So this is a very small difference, which means that your equipment would need to be able to calculate Coulombic efficiency and each of its constituents to better than 100 ppm of accuracy and be very precise about it as well. I'm going to jump to this slide here where I'm showing a bunch of different types of cyclers that are available in the market. These are very common types that we've got in our testing labs here, and that a lot of you will probably have in your testing labs as well. And showing just what consistent cells, these are all tier 1 cells. There's 8 tested in each of these groups for 20 cycles of charge discharge at low rates. In these cases, we're charging them at low rates to remove the effects of kinetics that introduce sometimes some noise into the system. And looking at the spread of what the Coulombic efficiency values are for those cells. And you can see this system here, the NOVONIX UHPC system, has the spread of only 40 ppm between all these identical cells. And some of these other systems are in the thousands of ppm. Although these systems are really great for doing long-term cycling and seeing trends over time, for doing really early prediction and really detecting some of these additional mechanisms and being able to identify and split them out into like fade and these other slippage-based mechanisms is only really possible with certain types of equipment. So I'm going to go back up to some of these slippage-based mechanisms and really look at what they mean in practice when we're looking at our data. So if we think about one cycle of a cell, looking at cumulative capacity over the x-axis here versus voltage, so not zeroing once we reset charge and go to discharge. If during our charge cycle, we count these additional mechanisms happening, these additional electrons that are going to go through our circuit due to these slippage mechanisms, we're going to count a little bit more capacity than the lithium we're actually moving across the cell. And then during discharge, we're not going to count all of those electrons again. So we're going to miss out on counting them because they are self-discharge mechanisms. So we're not going to end back at 0. The subsequent cycle, we're going to count more electrons than that previous discharge because we're going to count a lot of those slippage-based mechanisms again. So what this looks like in a lot of cases is over many cycles, our voltage curve kind of shifts to higher and higher capacity because we're overcounting electrons during charge and then not catching them on discharge. And if we do this accurately enough, this is what we call charge endpoint capacity slippage, where we put a pin in the map at the end of our first cycle and over time just track where that endpoint is. So this green arrow and this black arrow in terms of a cycle metric can turn into a plot like this, where every cycle we're tracking where that endpoint is, how fast it's moving. And that can relate to the rate of these reactions that's occurring. So in this experiment, we had additive 1 here, which is vinylene carbonate in identical cells, as additive 1 plus 2, which is vinylene carbonate and propane sultone. Propane sultone is well known to mitigate reactions happening at a cathode, especially in higher voltages, higher temperatures in NMC graphite cells. So you can also see that these cells here, there's duplicate cells in each of these groups, and you're very consistently able to measure this rate of these additional reactions if you have the precision and accuracy to track these endpoints. And so this gives us this additional cycle metric that tells us about kind of unique subset of reactions that are more or less invisible to capacity fade. So I'm going to stop for a second and ask a question. Is charge endpoint capacity slippage a new metric for you? Is this something you've used before or maybe read about, especially in Dr. Jeff Don's papers where he talks about UHPC and using this endpoint slippage? Or is this a fairly new concept and cycle metric? I'm going to look over at the questions just for a second. Yeah, so there's a couple of questions about calculating and estimating slippage. And I think I answered a bit of that question in how it's calculated. But yes, there's a relationship between all of these metrics in terms of finding your charge and discharge endpoints and really using them to either calculate Coulombic efficiency or fade or slippage. You can derive all of the equations from one another, but really just by tracking where your endpoints are every cycle, you're able to do this. Yes, and the question about zeroed capacity, I think that was on the previous plot. That's actually cumulative capacity that was being plotted there. So sorry about the confusion. Okay, so we'll move on here. So I want to highlight the way ultra-high precision coulometry works is really it goes back to when before I was talking about our raw data and how important it is to have accurate and precise raw data. Otherwise, those errors or uncertainties over and under counting propagate through into those cycle metrics like Coulombic efficiency. So in this plot, I'm showing multiple different cyclers, the same ones that were shown in that CE diagram, showing the spread of all these different cyclers. And you can see there's a big difference between things like cycler 1, which has fairly good resolution or precision, but poor accuracy. It's not accurately hitting the set point that we're trying to apply to the cell. Whereas cycler 2 and 3, you can actually see the resolution of these cyclers is limited by, say, this 16-bit precision that it has, or this 8-bit precision that this cycler has. So when you have this bit switching between these points here, it means that any time you're, say, in this bit, you may be overcounting, and then here you may be undercounting. And that error gets aggregated over time and integrated into your cycle metrics. And so that's why in some of those plots, there was a lot of noise, a lot of inaccuracy in some of those measurements. Whereas in systems that are capable of these much better than 100 ppm measurements, we're able to get these really good cycle metrics. So I'm going to blow this up into what more cycle metrics look like rather than just CE, so we can talk about slippage and fade. So across the top here, we have those same cyclers, and we show the Coulombic efficiency for each one, just splitting up that previous plot. So you can see cycler 1, again, has pretty good resolution, nice traces, but poor accuracy. Cell to cell, there's always an offset. If you were trying to look at the difference between one chemistry and another, all of these cells are supposed to be identical. And so if you're trying to get early insights, you won't actually be able to differentiate those cells. Whereas cycler 2 and 3, we start to get that noise from the lack of precision. With capacity fade, no matter what the resolution of your cycler, you're always able to see this over time, this trend as we're losing capacity. And this charge endpoint capacity slippage, remember how consistent the pair cells were in each of those experiments. And now all of these identical cells with these other types of equipment, they're not able to track that endpoint accurately. And what that means is some of these voltage curves are moving forwards in capacity and some of them are moving backwards, which means this isn't a cycle metric that can really be accessed on traditional types of cycling equipment. And you really need this better than sub 100 ppm precision. So I'm going to go into some case studies here. It's all well and good to talk about why it's really nice to have good data, but what can we really do with it? And I think that's really important. This is an experiment that we did here on our pilot line, looking at different types of cathode materials using 2 different NMC cathode variations, but everything else we were able to control using identical anodes from the same coating batch, using electrolyte from the same bottle, filled on the same day by the same person. And we see over really long-term cycle aging, this is almost 2000 cycles, the cells looked identical. And then all of a sudden, NMC 622 number 1 started going into this rollover failure, a really inconsistent failure. When we took these cells apart, there was lithium plating and localized dryout in these cells. And you can see this impedance really take off here, but there was no indication early on that this was going to happen. And this took many months to get to this state. So the hypothesis when we looked at these data is, okay, let's look back at our UHPC data. We should be able to see this happening because we know these cells are identical, except for the cathode. And so here, when we look at the UHPC data, we can see the Coulombic efficiency. There's a big difference here. 622 number 1 is a lot lower than 622 number 2. And if we split these up now, instead of just looking at coulombic efficiency, split them up into fade and slippage, we can see the fade is almost identical. And that's not really surprising because these cells were fading for thousands of cycles very similarly. But then the charge endpoint capacity slippage is almost, the rate of it is almost double in NMC 622 number 1. So this means that there's double the rate of these slippage-based reactions happening, which are leading to things like electrolyte dryout or salt depletion in the electrolyte that are invisible to things like capacity fade. So this can have really big implications if we can see this happening early on. Is this a useful thing to layer into things like lifetime prediction models? So I'm going to get into a lifetime prediction study that we did, which actually tried to come up with some generalizable lifetime prediction models. So we did this with a company called Sandbox AQ. We took a bunch of data that we had collected over many years and put it all in together and said, okay, let's try to use these unique UHPC metrics and get really valuable insights out of them, because we can actually use them to see very early these failure mechanisms that happen sometimes thousands of cycles out. So this experiment was about 128 cells that were tested. These are 3 different chemistries and vendors of cells, all with high nickel cathodes, but with varying degrees, either 0 or some silicon in the anode. And then we tested these under a bunch of different test conditions. We didn't use the same temperatures, the same voltage ranges. We really tried to turn on and off the different failure mechanisms that happen, going at room temperature up to 60 degrees. So 60 degrees, trying to really kick up the rate of electrochemical mechanisms happening and electrolyte degradation. And then operating in different voltage ranges, say from 2.5 to 4.06 volts, cuts out that last lattice contraction in high nickel cathodes, which can really mitigate some of the failure mechanisms that those high nickel cells may experience. And then doing the full range, and then also operating from 3.3 to 4.2 volts. So this is actually cutting out some of the silicon-based capacity in the lower states of charge, so that we're not actually expanding and contracting the silicon and losing lithium to those SEI-based reactions. So this matrix of different these different testing conditions really gives us a challenging generalizable case to try to predict lifetime with. So Sandbox worked with us to take all of these data and create some machine learning models that would be able to take very early data and help try to predict what's going to happen later on. We did these 2 different methods of using some standard model features. Anyone familiar with lifetime prediction may have read papers by Severson. And this is using things like a delta QV voltage features as feature sets for these models. So looking at the changes of the voltage capacity curves over cycling, and then using the trend of the first 100 cycles of the discharge capacity trend. So use some early data and try to predict what's going to happen later. Now, especially in cases where we're turning on and off different failure mechanisms, what this leads to is pretty poor model prediction, because in some of these cases, we're really punishing the cathode, and some we're punishing the anode, and in some we're trying to mitigate those failure mechanisms. So this isn't really generalizable. And so when we add in UHPC features, so we keep these same pieces of information from the long-term cycle aging data and only use the first 100 cycles and layer in some UHPC metrics. And what we did here is we tested these cells slowly, again, to try to remove the effects of kinetics on the cells and harness the impacts of electrochemical degradation mechanisms that were turning on and off, both due to fade and slippage-based reactions. So when we layer in UHPC metrics like coulombic efficiency, slippage, fade to these machine learning models, we get really nice model prediction. And so a lot of these results are being wrapped up and written into some papers that we'll be publishing to really communicate how these models were built. But really, they're quite simple in nature, using just the first 100 cycles and some simple features and layering in high precision data in order to help account for over prediction and under prediction of data. So I'm going to ask a quick question here. based on what I was talking about, charge endpoint capacity slippage, these kind of invisible mechanisms, so to speak, would accounting for slippage-based mechanisms help correct over-prediction or under-prediction of typical cycle life models? So over-prediction being that the actual cycle life is less than the predicted lifetime, and under-prediction meaning that the actual lifetime was greater than predicted. Okay, great. So the answer is that this will actually help with considerably with over-prediction of lifetime. Because when these slippage-based mechanisms lead to something like salt dry out or electrolyte dry out or salt depletion, this can lead to sudden kneeing where these discharge capacity trends or normal voltage features may not pick up on these insights, especially with lower resolution. So when these sudden knees happen, this region here of where the model's over predicting lifetime, it's really going to help snap these back down based on those rates of these slippage-based mechanisms that are happening. So just to bring this full circle before we wrap up, DQDV, DVDQ with high precision capable equipment is, we were talking about a little bit about smoothing or oversampling of data in some of the questions earlier. And with really high precision data, this isn't really necessary because you can get very clean voltage capacity curves just because the resolution and the precision of the voltage and current are very good. So this is actually showing some plots of these different cell types with DVDQ and DQDV on a UHPC system. And I really like this plot here because it shows over 45 cycles the residual plot of the change in the DQDV between each cycle. So it's only looking at the charge. And so say this dark line here is showing the difference between the cycle 6 DQDV during charge and the cycle 5 DQDV during charge. You can see there's almost no noise in the signal, and even very tiny changes that are happening are present and noticeable here. And then over time, 25 cycles or 45 cycles of difference here, we can really see these big differences. We can actually use these as feature sets for lifetime prediction as well, and even see really good performance, whether we use 40 cycles of UHPC, which is only a few weeks of cycling, and 2 cycles of UHPC data, which is about a week of data to get cycles 5 and 6 and get really good cycle prediction. We're running out of time, so I'm just going to jump to my summary here. Really, the one thing I would like to drive home is that UHPC isn't really a technique, it's a whole family of techniques. It's really what you do with the data analysis and interpretation is what drives the value of this type of equipment and the insights that you can get out of it. So this can be used, we use it internally for material screening, manufacturing process development, for diffusion measurements, for lifetime predictions. It really, the use cases are endless. And we've worked to make high current models, integrate EIS, et cetera. I won't get into those details. If you want to learn more, you can always reach out to us. But I'm going to pass it back to Kevin to wrap things up and get some questions running.
Great. Thanks, Stephen. Appreciate it. So yeah, with that, we'd like to open up the floor for questions and we can try and answer some of those. And as we do that here, I got to find the right screen. We'll post one more question. I got to make sure I find the right screen to share here. Maybe. Bear with me. All right, there's the question but I will post all right, so there's the question. And with that, I tried to go through and answer, while Stephen was talking, I tried to go through and answer some of the QA questions. Obviously, I can't keep up, I can't type that fast. Hopefully you're able to get most of your questions answered. There's a couple people that were questioning just some of the terminology. Yeah, incremental capacity analysis, differential capacity analysis, DQDV, DQ divided by DV, that's all similar. People use different terminology out there for right or wrong, right? Just like how the battery industry hijacked anode and cathode and made them slightly different than what electrochemists think anode and cathode are. Here we are with different terminology. Unfortunately, we have to live with all of that. But let's see, are there any more questions that are coming in here? There was a question about, do you propose any specific filtering technique to remove any noise or uncertainty of collected data at the end of a test? So I'll just jump in on that because I responded here a couple times to a few different people with you really have to look at your cycler. This is part of the benefit of using NOVONIX equipment, but you really have to look at your cycler and see what the resolution of your equipment is. I see a lot of times people are recording at like data frequencies of 0.1 seconds and some crazy high frequency data collection rates and things like that. And the reality is that if you're recording at too high a frequency, you're just wasting space. A lot of times it's great to record by constant current charging steps. It's a great thing to record by a DV step. Eliminates the need for smoothing your DQDV curves. And then in potentiostatic steps and rest steps, it's great to record by some sort of DT value. You have to logically think about that in terms of what the resolution of your cycler is and those sorts of things. Once again, I wish I could give you one silver bullet of this is how you set up a test, and this is how you can collect all this amazing information on DQDV and UHPC. And you have to think about your system, the battery that you're testing, and also if you're not using a NOVONIX piece of equipment. And even if you are, you have to think about what the resolution of that equipment actually is.
Yeah, and I think I'll layer into that answer a little bit because it'll answer some of the questions here. A question here was cost comparison with respect to a Neeware battery tester. And the answer is a lot more expensive. And like I said in the slide where I looked at a bunch of different cyclers together, every cycler does have its place and have its use cases. I wouldn't put a cell on 1C, 2C cycling for 6,000 cycles for a year and a half on a UHPC channel, because the types of data I'm trying to get out of those tests may be different from tests that I'm trying to do for a week and detect really quickly some lithium plating that might be going on, or other effects that may be happening, or changes in DQDV after a few fast cycles. So it's really about what insights you're trying to get out of it, and then what equipment you want to use. Some equipment's really good for high time resolution as well, whereas other types of equipment aren't. And there's a big interplay between precision, cost, timing, that you can never have all of them in one system.
Yeah. There was a question in the chat that I think is really interesting, and I'll honestly have to think about this a little bit more. But somebody was basically asking, are there any special considerations or complications related to doing DQDV when cycling at constant power, charge and discharge? And the answer to that is going to be yes. There's definitely going to be complications. Because you're not really at a constant current then anymore, because you're at constant power, right? And that's something we didn't describe in the different types of settings, right? We talked about galvanostatic and potentiostatic, and there is constant power charging and discharging as well, right? So one of the things I would consider if you're doing constant power charging and discharging, and that's really important, is maybe going towards, and I might have to think about maybe a better answer to this over time, but my first thought would be this could be a really good way to use the pulsing, like either use the app protocol or GITT, because you could do those steps at constant power for a certain amount of capacity and then monitor that, because you're looking at a DQ and a DV, but you also have to realize that you're going to have kind of a combination of potential effects there, but because since the current is not constant, the transport and the kinetics are going to vary. But by using the static DQDV method, you're going to reduce the effects of transport and kinetics. So hopefully your analysis would be a little bit less convoluted, if that makes sense. So that would probably be the way that I would initially try and answer that question.
There's a couple questions about if this is going to be recorded and sent out, and yes, it will, likely sometime next week.
Yes. So there was another question here for DQDV and real world vehicle data. You can go ahead and plot it. You can do anything. In the real world, right, your current is really changing all over the place. I think there's potential to do DQDV or potentially SDQDV or something like that during your charging step, but probably during discharge where it's all over the place, I would say that the value of that is going to be significantly limited. something you just have to consider there. But that charging information of in-field data is actually a really great place to get a lot of good information, and I don't think that we're doing as much as we can do with that information right now.
Yeah, one more question I'll answer. The UHPC learn about BMS limits quicker than using normal cyclers. So defining cell limits, insights about aging. This was actually what inspired our lifetime prediction work, things for like warranty predictions under different applications and use cases, and how to, reverse engineer what the conditions should be limited to out of understanding the electrochemical implications of those applications. Yeah, so hopefully that helps with that question. We work on those types of projects all the time.
All right, there's a couple more questions here. Yeah, how does peak intensity change with respect to cycle and DQDV? Normally it decreases over time, and Voltaiq has some automatic techniques for extracting information on peak intensities as over many cycles. So you can plot it versus many cycles and see how that's actually changing. So normally it decreases. There are things where maybe, like I mentioned, you can have structural collapse or phase changes as the cell ages or something like that. And you could see a shift, and all of a sudden one peak becomes less intense and another peak becomes more intense. And there's a lot of variation there. So the only thing I'd say is that really just think through the theory. It's part of the reason that I laid out as much foundational framework as I did. And I even showed the Gibbs free energy equation and stuff like that. Is that hopefully as you have these questions, right, lean into trying to figure out what is actually this data telling me and try and understand, because there's a lot of clues tucked into that data. More questions about DQDV, peak shifts, and aging mechanisms. I'm curious to maybe get your take, Stephen, on if you have any more advice on that. But a lot of times peak shifts are a lot of times over potential driven. They can be new phases or like lithium going into new phases, but a lot of times peak shifts are over potential driven due to kinetics and transport limitations and buildup. And then peak intensity losses and changes can tell you where in specific phases where you're losing lithium from, or maybe gaining lithium to, right, in some cases. So looking at all those things can be helpful. I don't know, Stephen, if you have anything to add to that.
No, yeah, that's all I would say. Yep.
All right, let's see. Yeah, and somebody's saying peak area analysis not necessary along with DQDV. Yeah, obviously it's great. If I could tell you, hey, you could perfectly fit your DQDV peak and you knew that your peak fit was going to be accurate, I'd say do it every single time. I'd say it'd be really helpful, and you'd get a lot of, valuable information of, hey, this number of coulombs is coming from this phase, right? It'd be really powerful. The problem is that just like any sort of other spectroscopic technique or anything like that, right? Like it's convoluted, and there's these overlapping Gaussians and all sorts of stuff like that, and there's benefit to it. I don't want to downplay the benefit of it, but there's also inherent error and challenges associated with it as well. So when you do it, you just got to be careful and understand the limitations of the analysis that you're performing.
I think it's like thinking about equivalent circuit analysis in EIS. You can add 1 million circuit components until you get a nice perfect fit, but does it really mean anything? And one of the quotes that I'll always remember from Dr. Jeff Don was with equivalent circuit modeling is, you could fit an elephant. So he's just saying you could just add as much stuff until you could fit any shape. So it is, like you said, you have to be very careful in interpreting what the peaks you're putting in there really mean.
Yeah. I spent a lot of time when I was at the National Renewable Energy Lab doing fitting analysis for XPS. And there's a lot of things you can do to be really rigorous and really, careful with that. It just takes a lot of time. And so it's not something you're going to be doing at high throughput or to help you explain. It's a very specialized technique that you need to utilize at the right times. Just what we've been talking about with all of this, right? These things, UHPC, DQDV, pulsing, EIS, all these things are tools in your tool chest that you need to pull out at the right time to help you solve the problem. All right. Temperature and C rate. How does temperature affect low C rate, especially below 0 degrees Celsius? Is it more affected due to overpotential, or can we still see the thermodynamic effects at these temperatures? Yeah, obviously, yes, you're going to see the thermodynamics. You can definitely see thermodynamic effects, just like there's different phases at different temperatures on a phase diagram, right? That will obviously affect thermodynamics. Kinetics gets really limited pretty quickly in temperature limitations, which is a lot of times what lithium played out at low temperatures. You just have to realize all those different things. And part of the reason why I recommend really trying to separate out the effects of kinetics, transport, thermodynamics, that was part of what the paper that we just published on we called the app protocol. It's basically a pulsing protocol like GITT, like HPPC. It's a pulsing protocol, so it's similar to those, but it basically takes a new twist on it in terms of the way that you perform it and the analysis that you do, trying to separate out all three of those different components. Because yeah, temperature is going to affect all of them, right? It's going to affect transport, it's going to affect kinetics, it's going to affect thermodynamics. Obviously, you're going to be able to view that and see that in a convoluted fashion in DQDV. And then with some of those pulsing protocols, you can actually try and separate them out and get individual effects at the thermodynamic level, the kinetic level, and the transport level. Could be powerful and helpful in some cases. Once again, just another tool in your tool belt to help you try and solve those sorts of problems. You can fit an elephant. Yep, that'll be a good takeaway from this session today. All right. With that, I think that we will call this webinar closed. Thank you everybody for joining. We still have over 100 people here that are listening to all these questions, so I think that's fantastic. If you missed it at the beginning, this webinar is recorded and will be emailed out to those that were registered. So if you're here, you're registered, so you'll get a recording of that email or of this webinar in your email. And yeah, we look forward to hopefully talking to you all again soon. Thank you very much and have a great rest of your day.
Thanks, everyone. Thanks, Kevin. Thanks, Jessica.